Okay, we talked about several uniqueness theorems, and this is again the strength of the book. Griffiths has this sort of an extreme example of what happens. Suppose you have a charge plus and minus close by, and then minus and plus. They're very close to each other. They're being held, yeah, so that they don't fall into each other. But now you can, I mean, and imagine this is very far apart. I shouldn't have even drawn it here. I should have drawn it miles and miles apart. Yeah, so these guys literally don't even see that. Huh? What's that?
Every time I pop my neck, I don't know, she gets triggered.
When you pop your neck?
Yeah,
he
like,
does this.
Yeah, that is kind of creepy.
Yeah.
it's not creepy. It's just a lot of tension in my neck. I just got used to it. I guess it's bad. I don't know. Feels good afterwards.
You realize we're discussing neck popping on the video, right?
Oh, I'm sorry.
No, that's, so now what he says is, you connect it by a conducting wire. Yeah? What's going to happen?
Charges will distribute.
I mean, it's just two charges. This is positive and negative so close to each other. They're being attracted by Coulomb interaction. What's going to happen is this is going to come, well, or the electron is going to go over there, and it's going to neutralize. Because of the uniqueness theorem. If you have the total charge on each conductor, if you find a solution, then you have the solution. So I can put V equals 0 as a solution. Charges are 0 everywhere. So even though the attraction here is so close and strong, if it is truly a conductor, it'll neutralize. Sort of an extreme example of the uniqueness theorem. Yeah? And now, today, we'll use our uniqueness theorem to do a class of problems. Okay? It's called image theory. Image theory is by and large only useful for two problems. But these are problems in your textbook. So what you have is a infinite conducting plane. Well, I should, typically how infinity is suggested is by not drawing a straight line, but this is z equals 0. And it has an infinite conducting plane. And we're also introducing a new concept here. It's a simple one. It's an intuitive one. Yeah. I'm going to ground this. It literally means, well, the term comes from literally connecting it to the ground, but what it means is it has access to charges from the ground. Yeah? It's a conductor. And then what I'm going to do is take a charge and place it on top over here. Set distance d. And we're going to measure. Grounding it also means setting the potential to be equal to 0. Okay, we're going to set the potential here to be 0 and measure the potential relative to this everywhere. First of all, this is V equals 0. There are no charges here. So I'll tell you one thing that satisfies the Laplace equation is V equals 0 below for Z less than or equal to 0. The real question is, what's the potential above? Now, what's going to happen is, in reality, because you bring in a positive charge, the conducting plate is going to bring in negative charge from the ground. And this negative charge will be smeared. Yeah? We have to find out what that is. And the question is, what's the potential everywhere? Okay? So let's make one caveat to use the uniqueness theorem, because we will use a simple technique to find the potential. Let me also draw another diagram that will be more visual for us, because what we really care about is only, that's sort of a 3D perspective. We have a charge D, a charge Q. Okay? Now, infinitely far away on that side, this is only one tiny charge Q. And whatever this small amount or finite amount of charge can attract over here. So what do you expect the potential to be far away? 0. So potential here is 0, and potential approaches 0 for x squared plus y squared plus z squared approaches infinity. And this is, of course, when z is greater than 0. For z less than 0, we know, so here in this diagram, v is 0 here everywhere. Okay? So we have all the boundaries of the above region. This above region has two boundaries. One is this infinite plane where the conductor is. One is infinity. So both of those, the potential has been prescribed to be 0. Huh.
Why do we say x squared plus y squared plus z squared tends to infinity?
At infinitely far away. So I'm saying potential equals 0 in two areas. Well, one everywhere below, but also, let me write it this
Are
way.
you talking about a plane infinitely far away?
This is probably, when you go that way, V approaches 0.
Okay.
Because there's only, effectively one charge here, and whatever negative charges this can induce. Yeah? All right. So, and the question, of course, is what's the potential here? So, the uniqueness theorem says, the corollary of the first uniqueness theorem says, if you find a solution, then it must be the only solution. Yeah? And the condition would be the potential here must satisfy a Poisson equation for this charge, and the potential here must be 0, and potential at boundary at infinity must be 0. So let us conjure up something that isn't there. Let us just say, same D below. I'm going to put a negative Q. This is an image charge, but it's virtual. There's no charge there. Yeah? And this is only for the discussion above. The discussion below, it is v equals 0 everywhere. Okay? But let's forget the real problem and let's focus at this problem. Now, if these two charges existed, what would be the potential above? Well, it'll be kq over, so at any point over here, you would have, let me call this R, and let me call this R prime. I would have kq over R plus k times minus q over R prime, just the magnitude. Let's write that out in xy coordinate system. Well, R equals square root of x squared plus y squared plus z minus d squared. Is that clear, or should I? I want to clarify. Let me clarify. And let me change my notation. We call this R. For any point R, this is my separation vector. Yeah? R and R prime. So, this is R, and this is R prime. R is equal to R minus d z hat. Is that true? Therefore, this is equal to x hat plus y hat plus z minus d z hat. Therefore, the actual distance is x squared plus y squared plus z minus d squared see? This is nothing more than this minus that. Is that true? You're thinking, how is that true? This may be more clear. R is equal to d z hat plus, that should be more clear, right? You go this way and this way, you get to R. So then when you solve for R, it's R minus d z hat. Yeah? And so now this is just straight out algebra. Similarly, what is this? Well, if one is minus, the other one is going to be, yeah? And therefore, it just coincidentally worked out here. Potential is kq 1 over x squared plus y squared plus z minus d squared minus 1 over x squared plus y squared plus z plus d squared. Yes.
So this is the magnitude of R prime, right?
I'm sorry. Oh, R prime. Thank you. That is the potential. Let's see what are the things it satisfies. Note. 1. V at z equal to 0. What is that? Well, 1 over x squared plus y squared plus d squared minus x squared, no, d squared. So look, this condition has been satisfied. And need del squared v equals negative rho over epsilon naught, right? That's what del squared v is. But let me use you get the picture here now, so I'm going to scrap this. Minus del squared v equals kq times maybe minus del squared 1 over r plus minus kq times yeah? But I mean, now I'm just using the linearity property of the Laplacian. And this is kq. What is this? Four pi yeah? Minus kq 4 pi from, I realize that's from chapter 1. But now that I write it, you should recall it. And if you don't fully see it, go back to your notes. Yeah? Now, for z greater than 0, what is this? Over here, will r prime ever be 0? Where is r prime 0? Below. Therefore, negative del squared v, I have 4 pi and 1 over 4 pi epsilon naught, q over epsilon naught. This is exactly the physical charge we have. So it's a check. I realize it's been a while since we saw this, so ask questions. So what I'm doing here is, this is the Poisson equation. So we have to show that this satisfies that. But I'm not going to use this version, I'm just going to use this version. So negative of the Laplacian is the negative of the Laplacian of these two guys. One step at a time. Forget this KQ, I'm just copying this. From chapter 1, this by definition is 4 pi delta of the vector r, evaluated when the vector r goes to, the separation vector r goes to 0. There's a minus here, minus. This is again 4 pi delta where the separation vector r prime goes to 0. But remember, this potential we are writing only for z greater than 0. For z greater than 0, this will never be 0. Because what is r prime? The distance from below. So one more time, let me write the draw the diagram. That's a straight line. Ooh, it makes it worse. There you go. Negative q. This is r prime, and this is r. If you are over here, will r prime ever be 0? No. It will at least be d far away. So this is 0. Over here, will this ever be 0? Yes, precisely at the location of the charge. So the Poisson equation is also checked. There's one more check left. Can you tell me what's the next check I need?
Can I clarify?
Yep.
So with the direct function, you're always saying that it's everywhere is 0, but at that point.
Mhm.
And the reason why we can say, well, it's 0 because we will never be at that. For r prime, it's going to be 0 because we can never be
Yeah.
0 for r prime, meaning we're at that point.
At that point, we can never be here because we're talking about the potential above.
Always above, okay.
Yeah, we know the answer for potential below. What's the answer for potential below? 0. So we're not using this formula. Yeah? Yeah, so let me clarify. The image theory is only being used for the region where that other charge is. In the region below the conductor, where there's no charge, we simply say V equals 0. It meets all the conditions. There's no charge there. It satisfies Laplace's equation. It satisfies the boundary condition. It's unique. There's one more condition to be to be checked, which is what? As at infinity, very good, very good, very good. But that's clear, right? Clearly, as r and r prime goes to infinity, v approaches 0. So all three requirements are met. So what I'm going to do, I'm going to recap all of this after I erase this. But before I erase this, any questions?
So over here where we have, where we finished up for above.
Tell me when to stop. This one?
All the way at the bottom.
All the way at the bottom.
What
Yeah.
is that telling us?
Oh, this is what Laplace's equation must satisfy. In our case, we have one charge located at that. So it better be that. And we just showed that it's that just by recalling this formula. As far as we're concerned at this point, you can always, and you should, go back and verify where that argument came from. But if you don't, that's okay. You can take this as a formula. We have already shown it in class. Yeah? Okay. Any other question? Because, just lack of space I have to erase. Yeah.
So what do we actually find?
Yeah, that's what I'm going to do. But is the math clear? Yeah. So what we have found is the following. For z greater than or equal to 0, v equals kq. I'm just copying that formula down. X squared plus y squared plus z minus d squared. Like this is 1/2. condition, satisfies all the conditions of the uniqueness theorem. THEOREM. And is hence the potential everywhere. That is what we have shown. If you have a solitary charge above an infinite grounded conducting plane, yeah? This is the potential everywhere. Notice, this is continuous. When Z equals 0, this potential becomes 0. And V is also 0 below. So potential is continuous. So as I told you, when you ground it, it's going to attract negative charges over here. And the question is, what is the negative charge? What's the negative surface charge density? So for that, you recall E perp up minus E perp down equals sigma over epsilon naught. This guy is negative gradient of V using the up formula, but I don't need all of it. I just need the perpendicular component. Yeah? This is 0. Therefore, sigma equals negative epsilon naught dV dz correct? I have to erase the diagram and redraw it if necessary. Otherwise, I'll be cluttering up the argument. So, let's find dV dz using this guy. I have k cubed. Then the derivative of this with respect to z. So what do I get? It's something to the minus 1/2. So I would get minus 1/2 times x squared plus y squared plus z minus d squared to the 3/2. And please make sure I'm doing this correctly. And the derivative of this, 2 times z minus d. Correct? Then I have a minus, and then I have another minus, so plus, then 2 times z plus d over 3/2, lack of space. This, oh, sorry, look, guys, I made a mistake here. This goes here, okay? Now let's evaluate at z equals 0. Twos cancel, z's cancel. I mean, not cancel, z goes to 0. I get what? D over here. What do I get over here? z goes to 0, also get a d. So I get a 2d over x squared plus y squared plus d squared to the 3/2. Yeah? Huh.
The half score?
Yeah, this cancels that.
Oh, okay, yeah.
And this minus cancels that.
Mhm.
That's no good. Oh, no, it is good. It is good. Therefore, sigma equals, k is what? 1 over 4 pi epsilon naught. So k times epsilon naught is 1 over 4 pi. Times 2dq over x squared plus y squared plus d squared to the 3/2. And of course, the 2 and 4 pi can be fixed. This is not the derivative of q, huh? So let me write this as qd. That is the charge density that the point charge attracts. Notice, it is a negative charge density. Let me see. I want to make sure I haven't made an algebraic error. I scanned it this morning, but you know, algebraic errors can. 2 pi, perfect. That is the charge density. I can write this in cylindrical coordinate system because x squared plus y squared, see the charge density, negative charge density decreases as distance because you can easily see minus 1 over 2 pi qd. This is s squared. So as the further out you go from where the charge is, the charge density is smaller and smaller. But then the question you might ask is, well, that's great. What is the total charge that this point charge attracted? What would be your guess? You know, you're bringing one charge above an infinite conducting plane. As a result, there's a charge density all over the infinite conducting plane. What's the total charge this one charge could have attracted? Negative q. Let's see. The total negative charge attracted by q on the conducting plane is given by sigma dA, right? Negative 1 over 2 pi q d 1 over s squared plus d squared to the 3/2 s ds d phi. D phi goes from 0 to 2 pi, and this is 0 to infinity. It's an infinite conducting well, this better give me 2 pi, and it does. I can confidently fudge. This phi is going to give me 2 pi, so I have minus q d. I can put 2s ds, then s squared plus d squared. 2s is my integration factor, right? So then what does it become? Minus q d over 2. This is this to the, that's minus 3 halves, right? So it becomes positive? No, minus 3.
Or negative 1/2.
Minus 0 plus 1.
Negative 1/2. So then I would get 1 over s squared plus d squared to the 1/2, then divided by
Negative 1 over 2.
e. Okay, I should do these things before. Let's see, I think it might work out in the 0 to infinity. I think it does. Look, q d. When I put infinity, I get 0. And lo and behold, when I put 0, I get square root of d squared. Martin's prophecy has come true. So the conducting plane attracts negative q. Just a nice balance of things. Isn't that neat? Calculate the energy stored in the setup. There are many ways to calculate energy. One is rho v dv, but in our case, we don't have a rho, we have a sigma v dA plus, don't forget that charge Q, the actual physical charge, times the potential it sees at that point. And this is the potential at V equals R equals D Z hat. I mean, this is the smooth version. So it's what? It's basically 1/2 QV. For the continuous version, Q is replaced by sigma dA. For the discrete version, it is simply that. Yeah? This is 0. Potential on the plate is 0. Q times the potential due to the, Q sees the potential only due to what? The negative charge, or yeah, right? And so that is, what's the distance? 2D. Where did I get easily 2D from? Well, it's the potential this guy sees is only due to this charge in the above region. But if this is D, this is D, it is 2D.
Why are we only talking about the potential on the conductor?
Yeah, I'm recalling a few things. See, there are many ways to compute the energy stored in a system. Viewed discretely, it is Q times V. Wherever there is charge, there are charges on two places in this problem. On the conducting plane. So Q usually becomes a rho dV, but for us it's a plane, therefore the Q becomes sigma dA times the potential on the conducting plane. Plus, then there's the other charge over here. So 1/2 times this charge times the potential this charge sees. Does a charge see the potential due to itself? No, it'll be infinite. 1 over R is infinity. It sees the potential due to this guy.
I
Yeah.
thought that charge area doesn't exist.
No, you're very right. But that is my potential. You're very correct. But that you want to do it, but you know the potential. The potential is the potential due to this charge plus this charge. You're just subtracting off this guy.
Yeah.
Whatever the net potential is, you subtract off the self-potential term. Yeah? Very good. A charge does not exist. So once you enter the matrix, you find out that there is no spoon. Yeah? How many of you have watched the original Matrix? Yeah.
Very long time.
Oh, you should periodically watch it. You know, it's a good late night movie. Get it on Blu-ray or something. It teaches you so much about life. Good. I can't do much. Griffiths has a little more discussion on energy, like a couple of lines. I urge you. So let me pinpoint that. Page 127. I urge you to just go through that and ask me any questions.